Okay, so with that, I think we're able to handle a more complex system like solders. So solders, as you might know, are metal alloys that are often used to bond or join two components together, usually other metal alloys, for example. The bonding action is accomplished by melting the solder material and allowing it to flow, make contact with the components to be joined, and finally, after cooling, by removing the heat source of the soldering iron, we end up forming a physical bond with the components. So at low processing temperature, the solder, it's desirable to at a low processing temperature of the solid, it's desirable for preventing heat and damage to the electronics. So that is, in other words, we want to be able to melt the solder at a modest temperature so that we don't damage the things around it. Okay, and for this reason, eutectic systems are desirable. So a eutectic system is a homogeneous mixture of two substances that has a melt point and can solidify at a single temperature that's lower than the melt point of the other two constituents. Okay, so let's look at a system that might have that. So that system we'll see is going to be the lead tin system. And we're going to see that the eutectic point, that is where the liquid, single phase field liquid, will transform straight into two solid phases, happens at a eutectic point as defined by the coordinates of 183 degrees C on the vertical and a concentration of tin for the x-axis dimension there of 61.9. Okay, so at those coordinates, we have an equilibrium between what's at right and what's at left. So that is right at the eutectic point, the liquid is in balance with forming alpha solid and beta solid. Okay, and so typically the beta takes on the form of something like a precipitate, and so it'll provide things like ionic compounds or ceramics. And as we saw earlier in our work, these often act to prevent shear motion and plastic deformation, and so these are often used to harden a material. So eutectics, this explains how the eutectic becomes hard, because we form that second phase that is a precipitate, and it becomes very difficult to shear across those particles that have generated by reducing temperature at this composition but lower than the 183. Okay, so let's take a little bit closer look at that. So here's a system between copper and silver. This is the system that was used this was a system that was used for sterling silver, as you can see up here in the coin. And sterling silver is approximately 92% silver and about 8% copper. And Norman silver pennies change designs approximately every 3 years. Two-star design, as we see here, is thought to be the origin of the word sterling, because of the sort of two stars there in the time of William the Conqueror, about 1080, at the year 1080. Okay, so in this system, we have a binary eutectic system. So that is the two components. We know that they are copper and silver. And we're expecting a eutectic point, that is where we transition from liquid to two solids, at a point that's lower than the melt points of the two independent systems. So way over here we have pure silver, if you recall, and we can look for the transition from liquid to solid. And so here's the melt point of pure silver, and we can look over the same to the pure copper over here, and the pure copper system's melt point is right there. The eutectic point we'll see is where we can transition from pure liquid into two different solids. And so we're seeing that eutectic point right here. So So clearly the y-coordinate for that point near 800 degrees is lower than the two former melt points of the two independent components that made up the binary system, silver and copper. Okay, so hopefully you can see that the melt point here is at approximately 800 and maybe about 70% silver. Okay. So the type of phases that are present throughout the composition or phase diagram, we know the liquid. We saw that there are two solids, an alpha and a beta form. There are also some other territories in here. So we have an area where there's liquid and alpha in this white wedge area. And complementing that across across the liquid to the other triangular area, we have a liquid and a beta phase. At the extremes of that, where we have very low silver content, we have a pure alpha region. Okay, so this would be like pure cubic metal of copper. And at the other extreme, in pure silver, we would have the pure beta phase, which would be the cubic pack system of silver. Okay, so those two former constituents, the alpha, they're going to be that face-centered cubic copper, and it's going to be a substitutional solid solution where it's mostly copper, as we can tell. So it's going to be, on the order of maybe 5% silver and makeup of copper. And then at the other extreme, to the beta, at the very other end of the graph, we've got, again, that same lattice, which is explaining why their two metal atoms are compatible, so FCC. And here, again, we're going to be FCC in silver with makeup on the order of 5% copper this time. Okay, and then we've seen our eutectic point already. And so it turns out the coordinates for that are at the temperature of 779 and 71.9% silver. Okay. So, putting more to the understanding, so at that eutectic point, we have the eutectic reaction, where the liquid, with its concentration, so we know that is roughly 71.98% silver, is going to be in balance with the alpha and the beta phases that are both solids, okay, per the definition of our eutectic. One liquid forms two different solids, okay? And so we can ask the question, what is the concentration of silver in the alpha and in the beta? Well, again, we can use our tie line to help tell us this. So the concentration of the alpha that forms, we'll use a tie line that's just below that point to help us there. And so if we're interested in the alpha phase, again, we'll just simply go all the way to our intersection point, and it meets the alpha at about 8%. So we're expecting the alpha phase to have 8% silver. Similarly, if we're interested in the beta, this time we'll walk to the other part of the tie line, and we'll go and meet up with the beta phase, and so we strike that at the 91.2%. So the beta phase is going to be 91.2 weight% silver. Okay. And weight fractions for these two materials could be determined using the same approach that we had before. Okay, so hopefully you've seen here that a liquid that was homogeneous in the dispersal of the silver, upon cooling across the eutectic point, generates an alpha particles and beta particles coexisting throughout the bulk solid, so two separate solids with two different amounts or balances of silver, one being very low, 8% silver, the other being much higher, more like 91%. So clearly alpha and beta are different solids given their chemical makeup.